About the post-processing when you're using additive manufacturing method, like shrinkage, mechanical properties of manufactured part when compared to subtractive method. Okay, that's a huge, I mean, it's like a 1 year effort in that question. But yes, whoever has asked that, we do need to, depending on the application. Supposing you want to use it, I think there was some example cited for a small consumer good, for example. Then obviously you're not so worried if it's a door handle or something like that. But if you're looking at the examples I gave for aerospace or what Mr. Anil Kumar gave for space, I think then we need to look at heat treatments as necessary. I don't know if things like residual stress was as addressed before, but that's a huge one of the biggest challenges in powder bed fusion technology is residual stress management. Not so much in electron beam technology. So definitely we have to look at dimensional tolerance, which you're talking about shrinkage. We have to look at macroscopic or microscopic defects and thereby mechanical properties. And moreover, I don't again know because I didn't attend the second in the series.
Yes.
But I don't know. Orientation is again a very big thing. Many of you know that. So it's not like in subtractive manufacturing. We are not so much worried. We get isotropic properties. Whereas in definitely in both direct energy deposition and in powder bed fusion, laser powder bed fusion. I saw somebody had asked a question, what is LPBF? It's just a nomenclature. You have to look at orientation effects also based on your application. But it's really not all that challenging or difficult. It's just that, you already have a baseline or a benchmark in your subtractive manufacturing. So I would say we are lucky that way because we have a benchmark. All we have to see is how much of deviation it is with respect to that with the post processing. Okay,
Sure, ma'am.
yeah.
Ma'am, do you want to take the second question?
Yeah, the question number 2 that you've sent is, do you think that machine learning based models to predict processing parameters is the way to go forward? The conventional design of experiments approach is lengthy and cumbersome. Again, depends on what alloy or what material you're talking about. If it is any of the, if it is for the processing parameter aspect, today for most commercial alloys that you have with any kind of machine, even if it's a new machine, I think it's a very short kickstart time. So Mr. Anil spoke, he said we are also going to use our in-house facilities as well as leverage outside. I also said the same thing. At least today in 2019-20, I think this is less of a problem in well-known materials. Now, if you want to do a niobium-containing alloy, somebody in the space making a cryo engine may want an absolutely brand new alloy, or if you want a completely new maraging steel, machine learning needs a lot of data. Remember, where will you get this data? So yes and no. So if in processing parameters, I'm not so sure machine learning is going to be effective because you need a lot of data to start with. However, if you want to use an optimization software for the actual part, because it's no longer SolidWorks and you need to see how to put the support structures, how to make conformal cooling holes so that it doesn't collapse, how do you get dimensional integrity, surface finish, then perhaps machine learning, because then you can avoid a large number of trials like you've rightly said. So it's not so much for predicting processing parameters. It is more for actually a part. I think answers. I think a lot of well-known people in the finite element world are already doing this in
Yes.
terms of topology optimization. There's also very good softwares, freewares that are available for trials. So I think topology optimization is what machine learning will help more than the process parameter aspect. At least I'm not a processing person, so please correct me if I'm wrong there.
Ma'am, do you think software like which reduces the DOE, like the design of experiment for developing a new alloy, will those be a bit helpful in the future for something like this?
Actually, we have to look at the ingenuity of those softwares. I'm still not able to understand from a material standpoint unless you do first principle calculations,
Yes.
how will you be able to, uh, you know, first principle calculation? By that I mean in terms of solidification physics, in terms of looking at dendrite growth.
Mhm.
People are doing that. Research level, national labs, Oak Ridge National Labs has done a lot of that. For example, they can even use, I won't call it software. It is a very under word for that particular, what they are doing. But that is based on physics-based modeling approaches, where they can even predict not just porosity or defects in terms of macroscopic density, but they can predict how you can tune the laser power, scan speed, etc., hat spacing to go from a equiax to a columnar structure.
Exactly.
But I'm not able to personally, again, that is my personal experience and opinion, how you can use empirical softwares to, that is a little difficult for me to actually comprehend, Anil.
Mhm. Okay. Okay, ma'am. Ma'am, one last question. One of the user, Mr. Abhishek Shrivastava has. Uh, can we maintain grain orientation aligned in one particular direction after heat treatment? So I think because you are the
Yeah,
materials person,
yeah.
so
I mean,
it's just
see,
a small question.
again, yes, I saw that question, and I have one more that you've sent me. So I'll first answer this one.
Mhm.
So it's a very, it again depends on the alloy. So what grain orientation are we talking about? As I said, there is an, for the powder bed fusion and the direct energy deposition. For many materials, like for example, Inconel 718, many of you will know that it is a well-known
Yes.
additive material. It has been tried and tested for a very long time now, at least 15 years now. So, in a material like that, if I use a direct energy deposition, it is very, very difficult to get an equiaxed or a polycrystalline structure. Whereas with a laser powder bed fusion, given the kind of lasers we have, let's say up to about 400 watts. I'm not talking about the laser tech machines with one kilowatt and all that, but so grain, what kind of grain orientation? So there are two things we're talking about. One is anisotropy of mechanical properties in along the build direction, transfers to the build direction at 45 degrees to the build direction, etc., etc. Because partly because of residual stress that is built in the powder bed fusion. The
Mhm.
other grain orientation is we are talking about is having uniform thermal gradients to produce columnar structures, such as directly solidified microstructure or single crystals, wherein you avoid, you only have preferential grain orientation. So I'm not sure which orientation he is referring to, but whichever it is, it depends on the type of additive manufacturing technology that we're using. So, for
Mhm.
example, in a very crack prone alloy, you may need to do some extra heating of your mild steel build plate in order to even be able to get equiax structure. So uh, I know it's, may not have answered, but grain orientation is a very specific thing, depends on the technology,
Mhm.
because it is to do with the way metals solidify.
Exactly.
Yeah,
Yes.
very specific. And if you tell about a specific alloy, then as I said, Inconel 718, whatever you do in the direct energy deposition, it's very difficult not to get a columnar structure. Now,
Mhm.
Inconel 718 is typically with a powder bed fusion technology or electron beam, completely different structures you get in terms of grain structures. So,
Mhm.
and in any case, very few applications in the kind of industries that at least myself and Mr. Anil works,
Yes.
we are talking of low temperature applications.
Mhm.
So, if it is a high temperature application, then you have to do a post processing heat treatment anyway, and that is usually in our kind of alloys it is solution and aging. So sometimes during the solution heat treatment you sort of destroy the as built structure. So
Yes.
yeah,
Yes, ma'am. Ma'am, the last question which I have sent you through message. Can
yeah,
you take that?
sure. So does I presume it's dispersoid powder. I'm not able to
Yes.
see the spell. Yeah, okay. Does dispersoid powder helpful to enhance the creep properties for high temperature aerospace applications? I'm not sure I understand this question. Whoever has asked, can you please translate it? What does dispersed soy powder mean?
Actually, the same person was asking me about creep properties in high temperature aerospace applications, and something like on turbine level, how it can be utilized.
No, no, but what is this powder?
Uh, if we can answer from for just on
The high
creep
temperature
properties,
cream?
it's
Well,
yes.
again, it depends on, it depends on the material. So let's take Inconel 718 again. If you're
Mhm,
going to use the powder bed fusion and you're going to do an AMS 5564 or whatever specification, SAE specification you have for solution and aging heat treatment, and you're able to get a microstructure that's very similar to a rod structure
mhm,
in in an ostensibly casting. Remember, any type of additive, laser based or electron beam based additive manufacturing, you're layer by layer, you're casting and welding, basically,
yes.
except that you're doing it at such a high rate of the order of a million degrees per second or a lakh degrees per second that
Mhm,
you may tend to have non-equilibrium um, structures that can come up. So in terms of creep, again, it depends on the grain structure. Fortunately, material science and engineering allows you a three-way prong approach where you can tweak the heat treatment to actually change the structure, which in turn will affect the properties. So I'm not going to, I'm not going to be specific, but I'll give you one example. You can use the non-equilibrium structures to, and we've seen this in practical in a cobalt-based alloy. You can actually make use of additive manufacturing and judiciously use heat treatment with inputs from metallurgists, materials
mhm,
engineers, and you can actually make it better than even a cast. But not, I mean, it's not going to be valid for every single alloy, obviously, but
mhm,
there is the nice, beautiful window, and that is the message I would like to give, that you can get, sometimes you can get better mechanical properties, high temperature properties. You don't have to go by the run of the mill and say what is this, the as printed structure along the build direction transfers. This is a mechanical property. There is a beautiful window that it allows in some alloys to be able to manipulate the phase transformations and the
mhm.
physical metallurgy to be able to give you better creep.